Hello, in this session I'm going to talk about matrices. Right, the singular for this word is matrix, the plural is matrices. Now, a matrix is, in mathematics, is essentially a table of numbers. So if I just make something up, like that, I have 2 rows of numbers here and 5 columns, right? Now, usually we would put a bracket around it, and that's what it often looks like. There can be more rows, there can be more columns, just a table of numbers. Now, matrices is one of these things where it is not easy, it's not obvious what it is used for. And in fact, when I first learned about matrices, I've very little idea why we need to learn this and what we can use it for, although we will see one example afterwards. But it is only later when if you actually go into a science or engineering or a subject that needs more mathematics and more calculations, then you will find that matrices becomes very useful when you need to do more complicated type of calculations. But at this level, at high school level, you find that a lot of the time you'll be learning about some rules on how to calculate things with algebra, with matrices. You'll just be learning rules about how to add, multiply and subtract them, and you just have to treat it as a kind of a game, although it might not be something that you enjoy. But that's the idea. Well, most of the time we'll be learning some rules to use, except that towards the end of the session, hopefully, I'll have time to explain an example where you can actually use a matrix to solve a simultaneous equation. And that is the main use that we'll look at at O level. Right, so we have one example of a matrix here, and in order to learn more about it, we need to learn some words, some names to describe matrices and some notations as well. Okay, so I've already mentioned 2 terms which are often used. I call each of these vertical set of numbers a column, right? So that would be called a column. So we have 3 columns here, and this horizontal numbers is called a row, this set of horizontal 3 numbers. So that means that I have 3 columns in this particular, this example, and I have 2 rows. Now you can have any number of columns and rows, and the kind of matrix that we will look at most often at O level are matrices that have 2 columns and 2 rows. Right, so if I write this down, say 216 minus 3, like that. So there are 2 columns and 2 rows, and we call that a 2 by 2 matrix. So we call this a 2 by 2 matrix. We can also write it as 2 times 2. Alright, so for example, that would be a 2 by 3 matrix. So this is a 2 by 3 matrix. That's a 2 by 2 matrix. Okay, so we've learned the terms row, column, and we've learned the term 2 by 2 matrix. Right. So, next, if we now focus on the 2 by 2 matrix, there are different types of 2 by 2 matrix depending on the numbers that you have there. Now, one of the simplest kind is where all the numbers are 0. Can't get simpler than that. And this matrix, this type of matrix is called a null matrix. Null as in N-U-L-L, null, for nothing. So that's a null matrix. Okay, now another term that you'll learn is that if you compare these 2 matrices, you see that obviously they have different numbers of columns and rows, but one of the obvious difference, if you just look at it, if you just look at the 2 visually, is that this looks more like a square and this looks more like a rectangle in arrangement. So this is sort of longer this way. Because this is 2 by 2, there are the same number of rows and columns. In for this one, you have more columns and you have fewer rows. So because of this, the kind of shape that it looks like, we call this a square matrix. Alright, so that's not the square matrix, but we don't call it a rectangular matrix either. We just don't call it a square matrix. But if you have the same number of rows and columns, you call it a square matrix. So it doesn't have to be a 2 by 2 matrix. It can be a 3 by 3, 3 rows, 3 columns. As long as you have the same number of rows and columns, it's called a square matrix. And the next kind of matrix is when only the numbers along the diagonal, if you imagine that this is a square, then you can draw a line from one corner to the opposite corner, that's called a diagonal. So if only the numbers along this diagonal is not 0 and all the other numbers are 0, we call this a diagonal matrix. Right, diagonal as in diagonal of a square. A diagonal matrix. Now finally, there's a particular type of diagonal matrix in which the diagonal elements are all equal to 1. Now this type of matrix is called an identity matrix. And we will see that this identity matrix is quite a useful thing afterwards. So we have learned a few of these terms, and you should remember this because we would be using these terms in the rest of this session. Okay, now what can we do with matrices? Well, for a start, we can add them. So let's have a look. Adding. So suppose I have two matrices. Like that. I can add two matrices provided that both have the same number of rows and columns. So let's see how I would add these two. Now the way to add a matrix is simply to add the corresponding numbers. So if I start with this number 1 in the first row and first column, I would add it to the number in the other matrix that is also in the first row and the first column. Alright, so in this case I would add 1 to -2 and I'll get -1. Right, and I simply do it for each and every one of the numbers. So I would add 3 to 1, I would add -2 to -1, and 4 to 3. Alright, that's it. And you can imagine how we would do subtraction, pretty much the same idea. So let's try that. Right, in the same way, we take 1 minus -2, be careful of the signs, that's 3, 3 minus 1, 2 minus 1 minus 1, it's minus 3, and 4 minus 3, that's 1. So that's simple enough. And what if you have more than 2 columns and rows? It's exactly the same, you just add the corresponding numbers. But remember, it is very important that in order for you to add or subtract two vectors, they must have exactly the same rows and columns. Otherwise, you cannot add them. There's just no rule for doing that. Okay, so adding and subtraction are simple enough. Now, we're going to look at multiplication. That's more tricky. So what if we need to multiply those two matrices? It's easy to imagine that since we add a number to the corresponding number, we would just do the same for multiplication. But unfortunately not. We don't multiply corresponding terms. Now there is a slightly more complicated rule for multiplying two matrices. And here's how we do it. Now first of all, we would expect that if we multiply a 2 by 2 matrix by a 2 by 2 matrix, we would end up with a 2 by 2 matrix as well. So I would expect to get 4 numbers in the answer. Okay, now how do I get the first answer? Now in order to get the first answer, the first number there, I need to do a calculation using the numbers in the first row there and the first column here. I need to make use of those numbers. So in order to get the answer for the first row and first column of the answer, in order to get this answer, I need to make use of numbers from also the first row and the first column. Alright, the first row of the first one and the first column of the second matrix. Right, and the way to make use of these numbers is that I must take the first number here and multiply by the first number there. So let me do that first. 1 times minus 2, that's minus 2. And then I must take the second number multiplied by the second number. 3 times 1, which is 3. And then I must add them. Okay. Now to get the next number, that will be the first row and the second column, I need to make use of the first row here and the second column there. And then I would repeat the same idea. I would take the first number multiplied by the first number, that's 1. I would take second number multiplied by the second number, that's 9. And add them. So let's press on. The next number here is on the second row and first column. So I would go for the second row here and the first column there. Right. And I would multiply the first numbers, minus 2 times minus 2, which is 4. And the second number, 4 and 1, which is 4. And add them. And for the last one, second row, second column, I would use the numbers from the second row and the second column. So minus 2 times 1 and 4 times 3. So this is how we get the answer. Then we would add up all of these to get each of the number. Minus 2 plus 1 plus 3 is 1, 1 plus 9 is 10, 4 plus 4 is 8, minus 2 plus 13 is 11. So there we have our answer. So as you can see, it is rather more complicated than adding or subtracting. Now it might seem a bit confusing, and the way to learn it really is by practice. Now, just to get the idea across, I'm going to make this look at a slightly more difficult example just to get some practice. Right, well actually it might be a slightly simpler example. I have two matrices here. So the first one is a 2 by 2 matrix, a square matrix that we are by now familiar with. Now the second one looks a bit different. There's only one column, right? 2 rows but only one column. that's also a matrix, a simpler one than that, with just the two numbers. And we can multiply this. Let's see how to do it. So let's try to apply the rules that we have seen just now. To get the first number, I would take the first row and the first column. Okay, first row on the first matrix, first column on the second matrix. And then I would multiply the corresponding numbers. So first number by first number is 5. Second number times the second number, that's 12. And then I must add them. Okay? Now, so I imagine that I would have a matrix there. Okay? And I might want to now find the next number. So this would be, say, on the first row and the second column. Okay? Now from the idea in the last example, if I want to look for the number on the first row and the second column, I should look for the first row, look at the numbers in the first row here and the second column there. Right? First row, second column, I would use first row and the second column. But there is no second column here, there's only one column. What this means is that there is no number there, there's no second column here as well. So in that sense, the size of this matrix depends on the size of those two matrices. So in this case, what it means is that this is all I have in the first row. There is no other numbers. Okay, so we can forget that. So that means that there is no second column either. So we would just go down to the next row, still in the first column, and so second row, first column means that I must now look at the second row here and the first column here. And I multiply the first number by the first number, the second number by the second number, and I add them. And these are all I need to do. 5 plus 12, 17. 15 plus 24, 39. So my answer looks like that. Right? It's a 2 rows by 1 column, a 2 by 1 matrix. And because this matrix has just a column, we often call it a column matrix or a column vector. Now, the reason why we call it a vector, we will learn in probably the next session. So for now, I'll just mention that. Now, an important thing that that we have noticed here is that, okay, just let me emphasize that point, is that the size of the answer depends on the size of the matrices that you start off with. So in this case, you see that we don't have a 2 by 2 matrix in the answer, we just have a 2 by 1 matrix. And the reason is because we have this 2 by 1 matrix there, even though we still have a 2 by 2 matrix there. Now if you remember, when I tried to find that answer there in the second column, I find that I can't because there isn't a second column there. So what this means is that the number of columns in the answer, okay, must be the same as the number of columns in the second matrix. That's a very important point. number of columns here is the same as the number of columns in the answer. Okay? Now how about the number of rows? You can, if you think about what we have done, the number of rows that we have here depends on the number of rows in the first matrix. Okay, so we now have a way, a simple way to decide, alright, to tell, even before you find the answer, to tell the size of the matrix in the answer, to tell what is the number of rows and columns. All you have to do is to look at the number of rows in the first matrix, and the number of rows in the, number of columns in the second matrix, and those will be the same for the answer. Right, number of rows, number of columns gives you that. So that's one thing. Now, another thing that is important is this. Remember that each time we try to calculate a number in the answer, we go to one row in the first matrix and one column in the second matrix, and we have to multiply the corresponding numbers. What this means is that you must have the same number of numbers in each row of the first matrix and each column of the second matrix. Now, the number of numbers in each row of the first matrix is just the number of columns. Okay, if you have two columns in the first matrix, that means you have two numbers in each row. And the number of numbers in each column of the second matrix is just the number of rows. Okay, now let me draw a line here. This has got nothing to do with that. So this means that the number of rows in the first matrix must be the same as the number of columns in the second matrix, in order that you can multiply them. Whereas the number of rows in the first matrix and the number of columns in the second matrix would tell us the size of the final answer. The number of rows, number of columns determines the answer. And the number of columns in the first matrix must be the same as the number of rows in the second matrix, in order that we can multiply them together. So this is an important property of multiplying matrices. For example, just imagine that instead of having this 2 by 1 matrix here, suppose I have 3 numbers there. Suppose that I have a 3 by 1 matrix there. Alright, 5, 6, and maybe 7, another number. Will I be able to multiply the two matrices? I will not, because if I have 3 numbers there, I have only 2 numbers here. And it's just not possible to multiply, because I need a corresponding number for each of this on the row and each of this in the column. Okay, let's move on. So that's the multiplying a matrix by a matrix. Now there is another kind of multiplication which is a lot simpler. So look. This is when you multiply a matrix by a number. So we are not multiplying two matrices this time, just a matrix by a number. Now this is a lot simpler. The way to do it is simply to multiply each number in the matrix by the 5 here. Okay, so I'll take 5 times 1 to get the first number, 5 times 2, 5 times 3, and 5 times 4. And that's the answer. So this is a lot simpler than multiplying two matrices. And I should also mention one thing about equality. What do we mean when we say that two matrices are equal? So let's say I have the numbers 1, 2, 3, 4, and I have the numbers 2, 1, 3, 4. Are those two matrices equal? After all, they have the same numbers. Alright, the order is slightly different, but the numbers are the same. Well, these two matrices are not equal. In order for two matrices to be equal, the corresponding numbers must be equal, meaning that the numbers must not only be the same, they must be in exactly the same order. Okay, so for example, if I have another matrix with the same number and with the ordering of the numbers the same, then they will be equal. So this is an important thing to remember. Now we are still on multiplication. There is another thing about multiplying matrices that we should be aware of. Now let me start with an example with just numbers. If I have, say, 2 times 3, I know that the answer is 6. Now, but what if I have 3 times 2 instead of 2 times 3? Well, clearly 3 times 2 is also 6, and we are all used to thinking that 2 times 3 and 3 times 2 is the same thing, no difference, right? Unfortunately, we cannot assume the same for matrices. Now let's have a look. Suppose that I try to multiply two matrices, say 1, 2, 3, 1, okay, and maybe 2, 1, 2, 4. Right. Let me try and multiply this. I'm going to do it quite quickly. So I would take 1 times 2, which is 2, and 2 times 4, which is 8. Okay, and then I would take 1 times 1, which is 1, and 2 times 2, which is 4. And then I would do 3 times 2, 6, 1 times 4, 4. 1 times 1, 1 times 2. And the answer is 10, 5, 10, 3. Alright? Now let me try to do it the other way around and see what happens. So I'm going to put that matrix here, 2, 1, 4, 2, and this matrix here. 1, 2, 3, 4. Sorry, 1, 2, 3, 1. Let's try that. Alright. 2 times 1 plus 1 times 3. 2 times 2. 1 times 1. 4 times 1. 2 times 3. 2 times 2. 2 times 1. And we add them. 2 plus 3. 4 plus 1. 4 plus 6. 4 plus 2. Clearly, if you compare the two matrices, they are quite different. And all I've done here is to change the order of the multiplication. Alright, I simply swap the two matrices around, put the second one in the front, and do the multiplication, and I end up with an answer that is completely different. So this is an important thing to be aware of. If you have to multiply two matrices, the order is important. Alright, for numbers, we don't care about the orders. 2 times 3, 3 times 2, they are the same. But for matrices, the ordering is important, and if you change the order, you could get a different answer. Now, you might not always get a different answer. In some cases, they might be the same, but quite often they are different. It depends on what the matrix is. But we just have to assume that they are probably different, and we cannot think that it is okay to change the order of the multiplication. How about when you add two matrices? Is the order important? No, it's not. If you are adding two matrices, then it does not matter. We have seen examples of adding matrices just now, and you are simply adding one term, one number in the matrix to a corresponding number in the matrix. If you change the order, you just change the order of the addition for the corresponding numbers, and that makes no difference to the answer. It is mainly because multiplying matrices follow more complicated rules, and that actually it is because of that you could well end up with different answers. Now, I've talked about adding, subtracting, and even multiplying. Now, I have not talked about dividing. In matrices, unfortunately or fortunately, there is no simple way to divide two matrices. You might imagine that I can do something like addition, where you just divide the corresponding numbers, but not really, not when multiplication is actually more complicated, right? From what we have seen, you cannot just, when you multiply two matrices, you do not just multiply the corresponding numbers, you follow a more complicated rule, and there isn't a corresponding rule for division. But there is something related to division that we are going to look at. It's the idea of an inverse. Now, for numbers in arithmetic, we sometimes use the word inverse. If, for example, we have a number, then we can think of the inverse of 2 as 1 over 2. Now we have to be careful here again. There are different meanings for the word inverse. We have learned about In trigonometry, we have learned about sines and cosines. In functions, we have learned about functions and inverse functions. So you can have inverse functions, you can have inverse sines and cosines, and the meanings are different from what we have for just numbers. Okay, but so in this case, we are using inverse in the sense that we normally use it for simple numbers. So 2, if I have a number 2, the inverse is 1 over 2. Right. What about a matrix? If I have a matrix, can I do 1 over a matrix? Well, not really, but we can sort of do it. Now, to see what I mean, the idea is to develop this idea a little bit. If I have a 2 and I have a 1 over 2 as the inverse, there is something very special about a number and its inverse. The special thing is that when you multiply the two, the answer must always be 1. Now that's the same for any number. If I take the number 3, the inverse is 1 over 3, and when I multiply them, the answer must be 1. Okay, so that should be quite obvious. Multiply a number by 1 over its number, you are basically dividing 3 by 3. Right. So nothing very new here. Now I'm going to rewrite this slightly. Okay, I'm going to rewrite 1 over 2 as 2 to the power of minus 1. So the answer is still 1, or 3 times 1/3 as 3 to the power minus 1 is equal to 1. So the power of minus 1 for a number means the same as 1 over that number. So that we know as well. Now what if I have a matrix? If I have a matrix, let's say 1, 2, 3, 4. We can't do 1 over a matrix, right? There isn't a rule for that. Well, there isn't an obvious rule for that, I should say. In a moment you will see that there is kind of a way to do that. But what I'm going to do is this. I'm going to say, right, for number, okay, if I have a number 2, I can easily find an inverse, and then when you multiply the 2, you get 1. Now for a matrix, it's not so obvious, but can I find something like another matrix, okay, such that when I multiply it, I get an answer which gives me 1 in the matrix. There is, in a sense, but it's a little bit tricky. So first of all, the way to do it, the way that mathematicians have do it, is that we don't use an answer in which all the numbers are 1. We think of a matrix in which only the diagonal numbers are 1. Okay, so the idea is that mathematicians make up this new rule for matrix in which we think about a 1 for a matrix as a matrix in which the diagonal numbers are 1, the number along the diagonal are all 1, and all the other numbers are 0. Because they find that when they make up such a matrix and think of it as the 1 for matrices, they actually have a name for it. They call it the identity matrix. Alright, sometimes also called the unit matrix. They find that if they think of this as an identity matrix like the 1 for numbers, then it's actually possible, not every time, but most of the time, to find a matrix here, to multiply by your starting matrix and give you this identity matrix. So they like to think of this identity matrix as corresponding to the 1 in number, and this matrix that you can find as an inverse of the first matrix. So there is kind of, by making up this identity matrix, there is kind of a similarity with simple numbers, where you just have 2 times the inverse of 2 gives you 1. For matrix, there is nothing so obvious, but there's something similar, in which we think of the 1 for matrix as this identity matrix, and then we try to find the inverse somehow. So the next question then is, how exactly do we find this inverse? There is another rule for that, or another formula for that. Now, to make it easier to write down the formula, I'm going to make up some notations to represent these matrices. Usually, we use a capital letter to represent a matrix. So I might call that this matrix A. And the identity matrix is often represented by the letter I. Okay. Now this matrix plays the role of the inverse that corresponds to the inverse of numbers. Okay, so this matrix is often represented by A with a -1. Now again, this is a special inverse. It's not just 1 over the matrix. It just means a matrix that will multiply to give you this identity. And there is a formula to find it. So we have made up these symbols here, and now I'll write down the formula that you need to use to find A inverse. So the formula is this. Suppose that A, the matrix A, has the numbers A, B, C, and D. So in this example, I've used 1, 2, 3, 4. But to make a formula, I make it more general. I change these numbers to A, B, C, D, so that you can still use the formula even if you have different numbers. Okay, so if the matrix A contains these numbers, then the formula for A inverse looks like this. It's rather complicated. So first, we write down these brackets for the matrix, and you need to take the 2 numbers along the diagonal A and D and swap them around so that we have D, A here. Okay, and then for the numbers B and C, you need to add negative signs to them. Minus B, minus C. And you need to multiply the whole thing by a number. And the number is 1 over AB minus BC. So that is certainly a little complicated. It takes some getting used to. Now let's see how we can use this to find this answer. Okay. Right. A, B, C, D in this example are 1, 2, 3, 4. So I would take 1 and 4 along the diagonal and swap them to get 4 and 1. And I would have 2 and 3, and I must add minus signs to them. Like that. Okay, and I must multiply it by 1 over, right, AD is 1 times 4 minus BC is 2 times 3, that's 6. Okay, so this is minus half 4 minus 2 minus 3, 1. Let me just complete this. So this would be, and the minus half I can multiply each of the number in the matrix. Minus half times 4 is minus 2, minus half times minus 2 is 1, minus half times 3 is 3 over 2, minus half 1 is minus half. Right, so this is the answer, or this is the inverse of A. What this means is that if I put this matrix here, then when I multiply those two, you will get the inverse. So I'm going to fill this in. That's minus 2. That's a 1. 3 over 2 minus half. Okay, now I'm going to leave it as an exercise to you to multiply these two matrices and convince yourself that you do indeed end up with the identity matrix. Alright, you should at least do it once if you are looking at matrices for the first time. So I did say that I will talk about an example of how to use all these things about matrices that you have seen. And this is how one place where matrix can be used, simultaneous equations. Let's have a look. Let's have a look at this example. We have two equations there, and we want to solve for x and y. Now we have already learned how to do this in a much earlier session in algebra on simultaneous equation. For example, if you add the left hand side and the right hand side, you'll find that in the left hand side, the y and the minus y cancel, and you end up with 2x plus x, which is 3x. On the right side, you end up with 2 plus 1, which is 3, and then you can simply solve for the x. So it's quite simple. Now we can also use the method of matrices to find the answer, and you'll find that it's quite a bit more complicated if you use matrices, and I'm going to show you how. Now along the way you might wonder, why, if it is so complicated, why do we bother? Now the answer is quite simple. It's because it gets less it's because you can actually make it it is something that can become quite convenient. For example, if you write this into a computer program and let the computer do it automatically. So it is a way to automate things, and you can also use the idea of matrices to make up simpler ways and faster ways to calculate the answers when you have many simultaneous equations. Okay, so we won't be going into all those, but this would just be an example on how to use a matrix. Okay, the way is to first rewrite these two equations using matrices. How can we do that? Right. The 1 and 2 is fairly straightforward. I would just write it as a matrix like that. In a column with two numbers, 1 and 2. Okay, so you can start to see an idea of how to do it here. These two, okay, let me just do the same. So again, a column with these two expressions. Right. Now in the next step, I'm going to write this in this way. I'm going to write the x and y down here, okay, and I'm going to pick out the numbers from here. So x plus y, I'll think of it as 1 times x plus 1 times y. 2x minus y would be 2x minus 1y. So I'm going to pick out these numbers 1 and 1 and put it down here. 2 and minus 1 and put it down here. And I'm going to say that when I multiply these two matrices, I would actually get this. Now, it might not look very obvious here, but remember the rules that we have learned for multiplying matrices. Think of what you would do if you multiply those two matrices. You would go for the first row and the first column, and you would multiply the numbers. So 1 times x gives you 1x, 1 times y gives you 1y, and then you add them. See, we've just got the first expression. And then for the second row, we go to the second row here. 2 times x gives you 2x, minus 1 times y gives you minus 1y. That gives you the second expression. So indeed, this is the same as that. And this is how we can take the simultaneous equation and turn it into matrices, and turn it into a matrix equation. Now once we have this, the idea is this. I can multiply both sides of this by the inverse of that matrix. One. Okay, let me write this out. 1, 1, 2 minus 1 x, y equals 1, 2. Okay, right. I've only copied out this equation here. Now what I'm going to do is I'm going to say, okay, I have a matrix times x, y, and I get that. Now, wouldn't it be nice if I can somehow get rid of that matrix? Then all I have here is x, y, and whatever I have there is the answer. So the way to do that is to multiply both sides by the inverse of this matrix of 1, 1, 2, minus 1. Okay, because if I can do that, then this inverse times this matrix will give me the identity matrix. Okay, and if you have an identity matrix, when you multiply an identity matrix by another matrix, you will always get the same answer. It's like taking 1 times a number, you always get the same number. So this is an important property of the identity matrix, and why mathematicians think of the identity matrix as something like the 1 for numbers. Now you can easily check that that is the case. If I multiply these two matrices, I will go for the first row and the first column. I will take 1 times x and 0 times y, which is 0. So I have an x here. And then for the next number, I go to the second row, 0 times x, which is 0, 1 times y, which is y. So I do indeed end up with just xy. So it's as if I've multiplied xy by 1 and I get the same xy. So that's the effect of the identity matrix. Down here, what I have here is the inverse of this matrix times 1 over 2. So now I must use the formula that we saw just now to find the inverse matrix. So if you can remember, if not, just rewind a little bit and have a look again. We must first swap the two elements on the diagonal. So 1 minus 1 becomes minus 1, 1. And I must add minus sign to the other two numbers. Okay, and I must do 1 over, this is a bit more complicated, 1 over this times this, which is minus 1, minus that times that, which is 2. So minus 1 times minus 2, which is minus 3. So there. So let's press on. Minus 1 over 3 Right, I'm going to try to calculate the answer here. In order to find this answer, for the first number, I must take the first row and multiply it by the column. Minus 1 times 1, minus 1 times 2, and we add them. Minus 2 times 1, 1 times 2, and we add them. Okay, we are almost there. Now I'm running out of space there, so I'm just going to write out the answer here. So minus 1 minus 1 minus 2 is minus 3. Alright, so minus 1/3 times minus 3. Minus 2 plus 2 is 0. Okay. Now I have a number multiplying by a matrix. So I would take the number and multiply it by each of these numbers, and then you'll find the answer. So that means that the x is minus 1/3 times minus 3, which is 1. So let me write out the answer somewhere. To clean this out. Let me copy out this dot here again. X, y is equal to that, which is minus 1/3, minus 3, 0. And I do minus 1/3 times minus 3, which is 1, minus 1/3 times 0, which is 0. So this means that x is equal to 1, and y is equal to 0. And as a final check, you can substitute these two, 1, 0 into here, to check that the left side is equal to the right side, that the equation is satisfied. And indeed there are 1 and 0, so 1 plus 0 is 1. 2 times 1 is 2, minus 0 is 2. So that's it. That's an application, a use of matrices. Probably not very useful if you want to actually solve a simultaneous equation, but you do get such questions in the exam to ask you to solve the simultaneous equation using matrices, and that's where it comes in useful. See you next time. We'll finish here.